Thank you very much. So 5 minutes, I'll see if I can run through this very quickly. Slightly different group of people than I'm accustomed to speaking to, so just a bit of background. My research is primarily involved in trying to look at space weather in terms of effects on the ground. And so the major index that I would use is something called DST. That's the Storm Time Disturbance Index, which is created by using magnetometers all around the planet. And so forecasting this DST index, which looks something like this is 1963 to 2006, is fairly important for geomagnetically induced currents and other such ground effects. The problem is that it's very difficult, as you know, to try to understand the motion of all the electromagnetic and plasma effects coming from the sun to the planet. We do have fairly good ideas about DST. When DST drops below -100 nanotesla, and that's these examples over here, then almost certainly we have massive geomagnetically induced currents and other effects. We have problems with satellites and so on. So that's just a good number to keep in your mind. And so what I did was try to use a simple, very simple idea. Basically, is there a storm tomorrow? The DST index has a cadence of 1 hour, and we have good data from actually 1957, a little spotty, but 63 onwards. So 1 hour cadence, and up to the present. And so what I did was I said, is there a storm tomorrow? Defined as DST less than -80, yes, 1, no, 0. I used a training set from 1963 to 2006, and then tested on later data. The inputs to my network, which was a temporal convolutional neural network, we're trying to take advantage of some of the well-known now fractal and multifractal nature of this very highly intermittent data series. And so I actually calculated fractal scaling indices for this, and then we put those scaling indices in. And then I use a method called measure representation. So it's taking a symbolic dynamics analysis approach to looking at the index. I don't have time to describe it, but there are papers that you can read if you're interested. But basically, we use a probabilistic forecast using patterns of previous events. So there's a temporal pattern that we try to follow. We put that in. So these are the inputs into the neural network. And then here is my architecture that I try to use. The reason this, I think, is helpful is because it captures some of the multi-scaling behavior in this. And so that was the idea, try to put some of the strange input into the neural network. Anyway, so here is the output. This is just the training showing you that training in blue and validation behave similarly in terms of success. And then red here are the forecasts, no storms, and storms. It's a little difficult. I hope you can see those little edges. So these are true positives where it's actually forecasting storm 24 hours ahead for DST less than -80.
James, sorry for interrupting you. Could you a little bit maybe compress your talk so
time
that
up?
we are, time is...
How much time do I have?
Well, 1 minute, and let's switch to
all right.
question session.
So what we found in compression was that we had a 80% correct, true correct forecast. However, if we consider DST less than -100, we got 94% success for 1 day ahead forecast using this simple method. So the exciting thing is we only use DST input to forecast the storms. And so the next step is, of course, to include things like solar cycle effects and solar wind as well. Thank you.
Any questions? Please, second row.
So DST is a proxy to define a geomagnetic storm, right? So I don't understand. You're just doing forecasting based on just DST numbers?
Correct. Yeah. Yep. So it's using past. So the idea is that the internal dynamics of the magnetosphere is not driven entirely by the solar wind. The internal dynamics has a memory of its own. So yes, coronal mass ejections are going to cause storms if they're halos. But there's all kinds of other things which cause DST to drop below -80 and minus, even the big ones. And so there's a memory effect. And so we capture that. The input that I put into the neural network, I used PyTorch, which is what I put in. That takes into account the multifractal memory. So there's long-term, there's patterns essentially which occur in terms of recurring cycles, which are not they're not periodic in any sense. They're multifractal patterns, and so the memory. Think of it as an unstable non-linear equilibrium, non-linear dynamical system. Non-equilibrium system. The system, if it's ready to explode, then sure, there are certain inputs. Coronal mass ejections will always cause the storm, but there are other things which will cause it as well.
Right.
And so this is capturing that.
I've just got one more question, follow up on that. So since you're taking data from 1970 till today, till today, right?
Yes.
Are you removing those time windows where you might have a CME interaction and it might have caused a DST going from -70 to, I don't know, -200? Because that can only happen when you have a eruption of CME or a high-speed solar wind. Then if you're taking that and if you're just looking at DST pattern from the past, it just, I don't know, it just...
Well, we've got 24, so the cadence is 1 hour, right? So we got 1 day ahead forecasts that we're doing over here. So forecasting right now for all other methods, so statistical methods and so on, they're very good with 6 hours ahead forecasts. 1 day ahead forecasts, they're not so good.
Right.
Okay, 1 hour ahead and so on. It's brilliant.
Yeah. And what's the train test split?
So this is the training set, 1963 to 2006, and then we test. I can't remember exactly what I used for the test, but 75% was training and test, and then the actual training and validation, and then the test was, I think it was 2000 and this is the training validation. That's the test set. So 2006 onwards. So we've got 14 years, 16 years where we tested that. Yeah, 2006 onwards.
Okay, thank you.
Mm-hmm.
I would ask if somebody has also questions now, so maybe better informally because we need to keep up with the schedule. And thank you very much, James.
Okay.
So we are